This is the third video in the series discussing the Walnut software. In order to really understand what the Walnut software does and how it does it, I strongly recommend viewing the first two videos before watching this one. Links to those videos are in the description. In this video I will actually demo the software, although, in truth, there's not so much to see. The functionality is mostly below the surface on the Walnut server, and the Walnut client does not even have a visible user interface. Also, be aware that the Walnut software changes constantly as things are added and removed in order to support specific FPath experiments. This means the version you download from GitHub may well look different unless you pick up a specific commit ID. I am showing the Walnut software as of version 1.04. Also, please note that the Walnut software, at this time, is not particularly productionized. It is a work in progress. This means that things like the IP address of the Beaglebone Black is hard-coded for now. It is trivial to change that in the code, though. Also, there are screen controls left over from previous experiments, which have never been removed. It is a research tool, and if I'm being honest about it, it is a bit of a visual mess at the moment. The basic substrate of the Walnut server and client is functional, though, and that is what I will demonstrate here. When you open the Walnut server, you will see a panel on the left. This is where the USB camera image appears. Over on the Setup tab, we can see the camera we are using. If there are multiple cameras, you will see a drop-down list here. These are automatically detected. In this case, we are using the Logitech C920 USB camera. Below that are the video format the camera offers. We have chosen to use the YU-Y2 format in a 640 by 480 frame size. The C920 is capable of much larger frame sizes, but using something like 1920 by 1280 really slows things down when it comes to image recognition, as there are just so many more pixels to process. Mostly this sort of resolution is just not needed, so good old 640 by 480 it is. We can see a summary of the selected camera options at the bottom. If we return to the main page, we can click on the Start Capture button to see the output of the webcam. On the screen of the Walnut server software, you can see the bed. Let me show you a global view of the apparatus so you can get some context. The experimental platform is the frame of an old RepRap Mendel 3D printer. You can see the camera at the top. Just below the camera is a LED ring light for illumination. The bed is directly underneath the camera. You'll note that the bed has an XY DC motor setup. If you think you're looking at Lego blocks, then you are right. I often use Lego blocks for experimental apparatus. They are extremely precise, cheap, and very useful. If you're interested in that sort of thing, please see the link to my Stego project in this video's description. In front of the bed is an old Mendel Electronics mounting board repurposed to mount the custom electronics required for various experiments. The Beaglebone Black is on the right underneath the green breakout board cape, and the two PWM motor drivers are mounted on a custom board on the left. You can see that all of the electronic boards are mounted on Lego bricks which slot neatly onto a thin Lego plate glued onto the MDF of the Mendel's electronics board. This keeps everything reasonably tidy, all the while enabling things to be quickly moved around as necessary. So let's return to the Walnut server now. You can see that the video capture has been running all the while I was talking and showing you the experimental platform. The current date and time, and experiment name, video number, and frame count are all injected into the video and placed as a discrete black band called a chyron at the bottom of the image. As discussed in the second video in this series, this effect is achieved by placing a custom Windows Media Foundation transform in the video stream. If I wish to record the current video, I can just press the recording button and the video stream will be duplicated and one branch sent to a file on the disk. Of course, there are all sorts of screen controls up here to handle the output directory location and file names and that sort of thing. As with the documentation chyron, the recording is handled by another transform. This transform duplicates the stream and sends one copy to the disk as an MP4 file. Because the file output transform is placed in the stream after the chyron is overlaid on the image, the chyron text gets written to the disk as well. Hopefully, you're starting to see that having control over the image stream in this way enables some very interesting and experimental options. Just wait, there's more interesting stuff to come. I will now turn off the recording. Having the recording enabled does not slow things down in any observable way, but the MP4 files get large, and there's no point in cluttering up the disk. Below the recording button are some screen controls I have implemented for various experiments. The stepper stuff is disabled on the Beaglebone Black at the moment, but the pulse width modulation controls are operational. These are the set of controls used to manually move motors on the XY stage. Let's click on PWMA and see the x-axis move. The speed of 50 here means 50% of the maximum speed. The DIR toggle pretty obviously just changes the direction. You can do the same thing with the y-axis. Remember from the previous videos that the Walnut server software running on the PC is not actually moving the motors itself. It communicates with a Beaglebone Black microcontroller running the Walnut client software. All that gets transmitted in this case is a command saying, turn on the A motor in this direction at 50% of the maximum speed. Once the command is received, simple action and behavior modules are activated on the Beaglebone Black, and these create the necessary signals on the appropriate ports. The motor driver boards attached to the I/O ports perform the actual movement. You saw these mounted on the left of the electronics panel during the global apparatus overview. If we go over to the Transporter tab, we can see a nice running log of the interactions between the Walnut server and the Walnut client. Speaking of logging, both the Walnut server and client create a log file on their local disk drive. This file notes the major events in the software. In addition, it is trivial for user-written code to output whatever information it wishes to the log file. This can be very useful for debugging. That was for manual control, but what about automated control? For automated control, the process is similar. The camera sends a video stream to the Walnut server via USB. The Walnut server accepts this stream, and its image recognition code figures out the coordinates of the colored squares and their color. As you have no doubt guessed by now, the image recognition code is located in yet another WMF transform placed inline in the video stream. This happens after the Chiron, but before the optional split to save the stream to an MP4. You can see that the image recognition system has recognized the red square because it's drawn a helpful little black cross on it. Although it is not enabled at the moment, the image recognition system is capable of recognizing multiple squares and circles. Also, the color and orientation of these do not matter. Nothing is moving at the moment because we have no green square present, and moving red onto green is the only thing the Walnut client is programmed to be able to do just now. Well, that and some manual moves. If you have total control over the contents of the video stream, you can do some interesting things. The target green square does not actually need to physically exist. It can be virtual, as long as you inject the green square into the video stream before the image recognition system processing starts. It will be treated as if it really exists. Let's use these controls here to make a virtual green square appear. We can see from the little black cross that the green square is recognized, and since we have both a red and green square, the Walnut software on the Beaglebone Black will be able to move the red square onto the location of the green square. The action is started by enabling the transmit option. Let's see this in action. If both the red and green square are detected and the transmit option is checked, a command will be issued to the Beaglebone Black to move the red square onto the location of the green square. The coordinates of the red and green squares are also transmitted along with this command. You will note that things are starting to move and the red square is moving towards the green square's location. If we change the location of the green square, the image recognition software detects this, and the closed-loop nature of the algorithm immediately redirects the toolhead to the new location. You can see that the Walnut software has detected the change of target, and the entire system has adapted. This leads to some interesting applications. If you could draw a green square on the frame, you actually already have the coordinates for it, so what's the point of drawing it in and getting it found by the image recognition code? Well, for a simple location, there is no real benefit. But say you draw in a shape. We turn off the green square. We turn on an overlay. The overlay is just a 640 by 480 PNG file with a green shape and a transparent background. It is placed on the top of each video frame by yet another transform. Now, we don't have a location, we have a path. The Walnut client software is not coded for it yet, but you can see where I'm going with this. Soon it will be possible to make a toolhead move over a virtual path or to react to virtual events on the screen. There is a lot of potential here, and I have a lot of ideas. Errors, as discussed in the first video in this series, can be removed or minimized by the closed-loop nature of the control system. The hardware simply does not have to be accurate in order to generate precisely controlled movement. For example, the XY stages here are built out of Lego blocks, not the most accurate movement mechanisms. Well, that's an overview of the Walnut server software. As I said previously, the Walnut software is a work in progress, a research tool. It is continually being modified for specific purposes and changes as the needs of the moment require. As and when other interesting functionality is added to the Walnut server and client software, I will try to post a new video describing it. You may also wish to look at the specific videos documenting the FPath experiments. Most of these will use the Walnut software. At the time of posting this video, there are 3 of them. You can find links in the description below. The Walnut software is open source and freely available for anyone to use. You can download it from my GitHub repo. However, if you're going to set up your own version of the Walnut software, you will probably want to contact me for assistance. There are a lot of things to configure, and some of them are not especially obvious. Thank you very much.